All right, so when we had left off on last Friday, we were looking at other resonant forms. And I had gone through a couple of things, and I think I went through it poorly, so I had actually derived everything instead of just relying on the textbook to do it correctly. So I'm going to revisit that stuff just real briefly here. So one thing that I didn't like about the textbook is that they only had the transformation in one direction. So here we have our series connection. Looking into this terminal, we're going to wind up looking at both the impedance and the admittance, and we'll see why in a moment. The quality factor for the series connection Q sub S is the magnitude of the reactance divided by the resistance. And then over here, we have our parallel connection. So let's call this R sub P in parallel with JX sub P. And looking in for ZP and YP, our Q factor is RP divided by the magnitude of XP. And looking at our admittances, that looks too much like a V for my taste. So we can see pretty easily that Y sub S is just 1 over RS plus JXS, multiplying through by the complex conjugate of the denominator over the complex conjugate of the denominator will give us RS divided by RS squared plus XS squared minus J XS over RS squared plus XS squared. Let's scroll down here a little bit. Looking in on the parallel connection, we just have 1 over RP plus 1 over JXP, which is the same as 1 over RP minus J 1 over XP. And so setting these two admittances equal to each other, we can equate the real part of each admittance to each other. So that means that we would have 1 over RP is equal to RS over RS squared plus XS squared. Flipping things over then, we have the relationship that RP is equal to RS squared plus XS squared over RS. And similarly, 1 over XP is equal to XS over RS squared plus XS squared. Flipping things over, we get XP is equal to RS squared plus XS squared divided by X sub S. So that's our transform in one direction, telling us how to get the parallel combination of elements if we know the series combination of elements. So now let's look at the impedances and figure out the transformation for the other direction. So if we look at ZS and ZP, we can see very easily that ZS is just RS plus JXS. We don't need to do anything to that whatsoever. The parallel connection, so I'm going to multiply those two impedances together. So in my numerator, I'm going to have J X sub P R sub P. And then in my denominator, I'm going to add them. So that's going to look like RP plus JXP, multiplying by the complex conjugate of the denominator over the complex conjugate of the denominator, winds up giving me RP times XP squared divided by RP squared plus XP squared plus J RP squared XP over RP squared plus XP squared. Now letting the real part of the impedances equal to each other, that's going to give us RS is equal to RP XP squared over RP squared plus XP squared. And the imaginary parts, setting them equal to each other, we're going to have XS is equal to RP squared XP divided by RP squared plus XP squared. So now we can transform both ways. We can also put things in terms of our quality factor. So let's go ahead and do that. So, yes. Okay. I'm trying to figure out how we can go back and forth between these two things, okay? So these relationships right here allow us to go from the series connection to the parallel connection if we happen to need it. And these relationships right here allow us to go from the parallel connection to the series connection. So we have developed a simple transform that lets us go either way depending on the situation that we're interested in. Putting things in terms of knowing the quality factor is just going to allow us to have a different method of doing the exact same thing, just in case we don't know what all of those things are. Okay. So in terms of the network Q factor, these transformations can be expressed as so let's start with our first transformation. RP is equal to RS squared plus XS squared over RS. So what I'm going to do is I am going to effectively pull out a factor of RS. So this is going to look maybe a little odd, but hopefully it makes sense. I multiply through by RS, and that's going to give me an RS squared in my denominator. And then I have RS squared plus XS squared, like so. Algebra okay there? So I'm just multiplying and dividing by RS. Well, the quality factor for my series connection is the magnitude of x divided by r, right? Well, if I square that, I would have xs squared, the magnitude signs go away because it's always going to be a positive thing, divided by r squared. And so I can have this look like rs times 1 plus xs squared divided by rs squared, which is the same as rs times 1 plus my quality factor squared. The derivation for xp in terms of q is pretty much just as straightforward. So xp is defined above as rs squared plus xs squared divided by xs. So we would have xs times rs squared plus xs squared divided by rs squared, or xs times 1 plus, oops, I'm sorry, this should be an xs squared down here. Getting ahead of myself, my apologies. 1 plus rs squared over xs squared, or xs times 1 plus 1 over squared. Looking at rs, we would have rp times xp squared over rp squared plus xp squared. So this is going to look like rp times rp squared over q squared, right? So I'm simply saying that since x squared for the parallel connection, let's scroll up here so we can look at it. So we have our parallel connection, right? So I'm replacing xp squared by transposing where I have xp and qp, right? So xp squared should be rp over qp. Go here, that's exactly what I've got here. Divided by rp squared plus rp squared over qp squared. And now I'm going to multiply by q squared over q squared, which is going to give me rp to the third power divided by rp squared times 1 plus q squared, or rp over 1 plus q squared, which makes perfect sense. Is exactly what we would get just by rearranging this guy here. Yes. You mean have a subscript on? Oh, thank you. And then finally, thank you for that. We have x sub s is equal to rp squared xp divided by rp squared plus xp squared. And I am going to replace all of my rp squareds with q squared times xp squared. That's going to look like q squared xp squared xp over q squared xp squared plus xp squared. So that's q squared xp cubed over xp squared 1 plus q squared. Xp cubed over xp squared gives me xp. Q squared over 1 plus q squared is the same thing as 1 over 1 plus 1 over q squared, and we have the exact form that we would expect based on our prior results. And then finally, for Q greater than or equal to 5, these reduce to RP is approximately equal to Q squared RS. Alternatively, we could say that RS is approximately equal to RP over Q squared. And then XP will be approximately equal to XS, which lets us directly substitute CS will be approximately equal to CP, and LS will be approximately equal to LP. All right. So same information that we covered at the very end of last Friday's class meeting, a little bit more detail about the derivations, and then also we derived the transform both directions so that we don't have to think about things. So what I want to work on now is a quick example problem. So let's look at the following circuit. So let's say that we have a simple RLC circuit that we are exciting with a 0.5 volts RMS signal at whatever the resonant frequency for this circuit is. And our circuit contains a 20 ohm resistor in series with a 10 millihenry inductor in series with a 0.01 microfarad capacitor. And I am interested in the following pieces of information. I want to know what my capacitor voltage magnitude is, or what we would expect it to be, and I'll talk about that in a moment. What my resonant frequency is, what my quality factor is, and what my bandwidth is. So this is just a straight series RLC circuit. There isn't anything fancy. We don't have to do any transformations here whatsoever, okay? So omega naught in this case should just be square root of 1 over LC. Which comes out to be 100,000 radians per second. Our quality factor can be written as omega naught, L over R, which would come out to be 50. Our bandwidth is omega naught over Q, which comes out to be 2,000 radians per second. And while we're at it, the magnitude of my capacitor voltage for a circuit that's being operated at resonant frequency should just be Q times the source voltage, right? So Q times the magnitude of Vs, so 50 times 1/2 is 25 volts RMS. We've established a baseline here, okay? So let me explain why I've established a baseline. This is what our analysis tells us what the capacitor voltage should be. What if I tried to measure this voltage RMS value, right? Our multimeters are capable of doing that. If I try to measure this voltage with a real multimeter, who knows what the input impedance of a multimeter is? What? So gigaohm is a bit high. I would argue somewhere between 100K to 1 megaohm would be a normal thing. So let's see what happens if we effectively put 100 kiloohms of resistance in parallel with this guy, representing the impedance that we would introduce into the system by connecting our multimeter, right? If we're trying to make a practical measurement on this system, to this point, we've always assumed that our measurement equipment isn't going to impact anything, but it very much can, okay? So our new circuit is effectively this, right? We're still operating, supplying half a volt RMS. Our angular frequency omega is 100,000 radians per second, which may or may not be the resonant frequency of our new circuit, by the way. We still have our 20 ohm resistor, our 10 millihenry inductance, our 0.01 microfarad capacitor. But now we have this pesky 100 kiloohms of resistance connected. Here's the capacitor voltage that the multimeter would see. Now, if I want us to find these same quantities, I could either do it using a whole heck of a lot of work, or I could transform this parallel network into a series network, and then use that to have essentially an electrically equivalent network that I can simply use these exact same expressions to calculate resonant frequency, quality factor, bandwidth, etc. Okay. So my series resistance, R sub S, should be R sub P times X sub P squared divided by R sub P squared plus X sub P squared, right? Well, R sub P is 100 kiloohms. X sub P is going to be 1 over, so let's see, 100,000 would be 10 to the 5 times 0.01 times 10 to the minus 6 farads, right? So 10 to the 5 radians per second, that's my 100,000, so that's omega, and then 0.01 microfarads is the value of my capacitor. We okay with that being the reactance of a capacitor? What it's been for 2 years at this point. Yep. Oh, sorry, you're right. It should be going on the X. So let me square this guy. Thank you for that. On the denominator, it goes on both of them. And we wind up getting here 9.999 ohms, approximately 10. Just as a heads up here. We know that our Q was greater than 5. So realistically, we could have used our approximation, I believe. Sorry, I'm spacing out. Let me look at the approximation. Yeah. So for just the RC network, what would the Q be, right? U sub P. So that should be RP over XP would be 100 kiloohms divided by 1 over 10 to the 5 times 0.01 times 10 to the minus 6 farads. Later. Q for just this parallel network right here with 100, well over 5, right? So we could have used our approximation. Q sub S should be RP squared XP divided by RP squared plus XP squared. So it's effectively this exact same thing. I'm going to be lazy. The result's the only part that actually matters anyway. Yep. Excess, thank you, yes. Weird. And this comes out to be 10.0, actually, hold on. This comes out to be 999.9. Dividing through by omega, we find that C would be 1.0001 times 10 to the minus 8 farads, which is approximately 10 nanofarads or 0.01 microfarads. The value of C didn't particularly change because our Q factor was so high. So our transformed circuit looks like this. Sorry, that first one was a 20 ohm resistor. My apologies. This is our voltage VC, so it's going to be the voltage drop over the 10 ohm resistor in series with the 10 nanofarad capacitor, right? Taking into account the influence of our measurement instrument. So omega naught is really the same thing because our capacitance didn't change and our inductance didn't change or didn't change appreciably enough to make any real difference. So 100,000 radians per second Our Q factor, though, is going to change pretty significantly, right? So now the R that goes into our expression for our Q factor, so we just had omega naught L over R. Earlier we had 50. Now we have 33.333 repeating. So our Q factor is only 2/3 as large as it was, which in turn is going to cause an increase in the bandwidth of our system, right? Our bandwidth, omega naught over Q, is going to be approximately 3,000 radians per second, up from 2,000 radians per second. So we've seen a pretty appreciable change in our bandwidth. But ultimately here, we're trying to measure our voltage. How is DC going to change? Well, what we'll find is that it actually comes out to be 16.667 with a phase angle of roughly negative 90 degrees. So the voltage that we would measure with our multimeter is not an accurate representation of what the actual voltage across our capacitor would be, because the impedance of our measurement device greatly impacted the structure of our circuit. Yes, sir.
How would you affect?
So you could use an oscilloscope where the probes have a significantly different impedance than the multimeter does, because it measures it in a significantly different way. We'll talk about a little something about that here in a moment when we're talking about filters and all that kind of jazz. I think what else we could do here. Yeah, I think that would probably be the easiest way. Another alternative way would be to just run a simulation, because this is just a simple RLC circuit, so it should behave pretty effectively. If you were able to accurately measure your inductance and your capacitance using an RLC bridge or something like that, you can get a pretty accurate model of what's going on. All right, so we've talked about transformations and all of that kind of stuff, making networks that don't quite look like a series RLC circuit or a parallel RLC circuit now look like a series of parallel RLC circuit. Let's now talk about scaling things. So in a lot of the examples that we've worked in this class, I've used ridiculously large values for capacitors, things like half a farad and all of that kind of stuff, mainly because it made the math easier to deal with. So now we're going to talk about how we scale circuits in order to actually use practical values. So this is particularly applicable in a lot of filter designs, especially when you look at tables for things like Butterworth filters, Chebyshev filters, and all that kind of stuff, which we're going to talk about. We'll do an example with a Butterworth filter today, but we'll talk about filters a bit more for Wednesday and Friday of this week. But effectively, if you look at electrical engineering handbooks and all that kind of stuff, it gives you a table where everything is effectively normalized to a specific impedance and a specific frequency, usually a radiant frequency of 1 radian per second, and usually with your resistor values scaled to either 1 ohms for the most generic normalized circuit or 50 ohms. And the reason why 50 ohms is used very frequently is because That's a very commonly seen impedance for transmission line cables, as well as the connectors for measurement equipment like oscilloscopes and all of that kind of good stuff. They typically have a 50 ohm input impedance to deal with. So we are going to scale things in both the magnitude and frequency. Okay, so let's start by looking at magnitude scaling because it's a little simpler to understand. So in magnitude scaling, our goal is to literally just increase the impedance of our elements while leaving the frequency completely constant, okay? So we know that the impedance of a resistor is the resistor value itself. The impedance of an inductor is just J omega L. And transversely, the impedance of a capacitor is 1 over J omega C. If I wanted to transform these impedances, I would simply multiply them by a scaling factor, okay? So we're going to call ZR prime our scaled resistance. And so this is just going to be Km times ZR, where Km is our scaling factor, letting us know how much we want to scale this thing. And so we would simply have Km times R, and from this, we can say that R prime, the scaled value of our resistance, is just Km times R. For an inductor, ZL prime is just going to be Km times ZL is J omega Km times L, and therefore L prime is just Km times L. And then lastly, Z prime or ZC prime will be Km ZC is Km divided by J omega C. So C prime is simply, sorry, I got this upside down, C divided by Km. So these are our magnitude scaling relationships. Let's see what impact they have on things like bandwidth, resonant frequency, and quality factor. So for a series RLC circuit, omega naught prime would be the square root of 1 over L prime C prime. L prime is going to look like Km times L. C prime is going to look like C over Km. So we have 1 over C, so that's going to look like Km over C, like so. The Km's very obviously cancel each other out. And magnitude scaling has no impact whatsoever on the resonant frequency, which it shouldn't. The whole point was that we kept the frequency constant. Looking at our quality factor, Q prime is going to look like 1 over R prime times the square root of L prime over C prime. So 1 over R prime is 1 over Km times R. L prime is going to look like Km times L. And then we're dividing by C prime, so that's going to be dividing by C, and it's going to put another Km in the numerator, like so. This guy cancels this guy, and we simply have 1 over R root L over C, which is nothing more than our normal definition for Q for our series resonant circuit. Lastly, looking at our bandwidth. So bandwidth prime should be omega naught prime over Q prime, which is the same as omega naught over Q, or just the bandwidth doesn't change. So effectively, for a series RLC circuit, using magnitude scaling has no impact on resonant frequency, quality factor, or bandwidth. Will that be true for a parallel RLC circuit? Absolutely. Because for a parallel RLC circuit, omega naught is literally the exact same relationship. Q is just flipped over, right? Nothing is going to change. Everything's still going to cancel out. And then if Q doesn't change and omega naught doesn't change, the bandwidth can't change for a parallel RLC circuit, right? So while we only explicitly derive these for series RLC circuits, every one of these statements is also true for a parallel RLC circuit, all right? So that's magnitude scaling, pretty easy. Yes, sir. Pretty much, yeah. So if we designed everything using 1 ohm resistors, 1 Henry inductors, and 1 farad capacitors, we can't practically find 1 farad capacitors, nor could we find 1 Henry inductors easily. So we'll apply this in just probably 8 minutes at this point, and it'll make hopefully a little bit more sense as the application. So now let's talk about frequency scaling. Okay. So in frequency scaling, our goal is to scale the frequency while leaving the impedance constant. Okay. So ZL prime would be J times omega KF, where KF is our frequency scaling factor, times L prime. We want this to be equal to J omega L. So from this, we can see that L prime is simply L over KF. Similarly, ZC prime would look like 1 over J times omega KF times C. Should be equal to 1 over J omega C. Let me make that J nicer. So we'd see that C prime is simply C over KF. Obviously, the resistance isn't going to change because it is frequency independent, so we don't even need to write anything for that. So now let's take a look at our... Yes, thank you. So for a series RLC circuit, omega naught is the square root of 1 over L prime C prime. So sorry, this should be omega naught prime. Will be equal to, so I'll just have LC in the in the denominator, and I should have KF squared in the numerator. So that's KF times square root of 1 over LC, or KF times omega naught. So our scaling factor literally just linearly scales our resonant frequency, which is the point of frequency scaling. Will it impact our bandwidth? Or excuse me, our quality factor? So let's see. So Q is going to be 1 over R. The resistance does not change, so that's why I'm just putting R and not R prime. We'll have L prime over C prime here. So this is going to be 1 over R times the square root of KFL over KFC. These guys cancel each other out, leaving us with just 1 over R times the square root of L over C, which is nothing more than Q. So it does not have an impact on our quality factor whatsoever, just our resonant frequency. From that, the change that we observed in our bandwidth will be omega naught prime over Q prime is KF times omega naught over Q, or KF times our original bandwidth. All right. Lastly here, let's talk about if we need to do magnitude and frequency scaling simultaneously. So just putting the results of our previous two topics together, our scaled version of R prime is just going to look like Km times R. Our scaled version of our inductance is going to look like Km over Kf times L. Our scaled version of our capacitance is going to look like C divided by Km times Kf. Our resonant frequency scales with Kf. Our quality factor doesn't scale at all. And our bandwidth scales with Kf as well. Yes. For this series Oh, absolutely. Sorry, yeah. So I didn't mention it specifically here. So omega naught for a parallel RLC circuit is defined exactly in the same way as omega naught for a series RLC circuit. So this one has to work. Our Q relationship would literally just be the reciprocal. So the KFs will still cancel each other out because this C and this L would switch. So Q stays the same. And then omega naught divided by Q is just going to give us this result either way. So I want to be clear. For a parallel RLC circuit, Q would be defined as the reciprocal of this thing, which would be R times root C over L. Like, don't use the series RLC equation for Q for a parallel RLC circuit, but the relationships here of how they scale do remain true. All right, so the last thing that I want to talk about today is to work an example that uses this stuff. And this is going to be our segue into filters, particularly higher order filters as well. So this will be our circuit of interest. And these are going to seem like odd values. So this is 0.765 farads for this capacitor. 1.848 henries for this particular inductor. 1.848 farads for this capacitor. 0.765 henries for this inductor. We have a 1 ohm resistor here. And then this is where our output voltage would be measured. So this is an example of a fourth order Butterworth low pass filter. Fourth order because we have 1, 2, 3, 4 discrete energy storage elements that can't be combined into anything else. I think we talked about this briefly in circuits 2 for those of you that had me, but why would we want to use a higher order filter? So the higher the order of the filter is, the more it's going to behave like an ideal filter with that brick wall response. Meaning we're going to see that it hits its corner frequency and then rolls off very steeply. So higher order filters roll off much steeper than a first order filter. And by the way, that should make total sense to us based on what we know about Bode plots, right? So if we have a Bode plot where we have a pole that's repeated 4 times, we should be rolling off at negative 80 decibels per decade instead of negative 20 decibels per decade, right? So that's exactly what's going on here. Now, this particular Butterworth filter is what's called a normalized Butterworth filter, in as much as it is designed specifically to have a cutoff frequency of 1 radian per second based on a 1 ohm load impedance and a matched 1 ohm series source impedance. Okay, so this is literally straight from the table that you guys will be getting before class on Wednesday for designing these batteries. So let's say that we want to scale this circuit such that omega naught is 50 kilohertz for a resistor value of 10 kilo ohm. So we're going to figure out what our component values should be, and then we're going to simulate both of these circuits in LT Spice to show that they have literally the exact same magnitude and phase response, except that one of them is shifted by 50 kilohertz. Sorry, this should be F naught because I gave you a linear frequency because we measure in hertz. My apologies. All right, so what should our magnitude scaling factor be based on this information? 10,000, absolutely right. 10 to the 4. So that's just going to be R prime over R. What should our frequency scaling factor be? Well, 2 pi times 50 kilohertz divided by 1 radian per second is going to look like pi times 10 to the 5. So if we call this capacitor C1, this capacitor C2, this inductor L1, and this inductor L2, what we'll find is that L1 prime will be Km over Kf times L1. So that's 10 to the 4 over pi times 10 to the 5 multiplied by 1.848 gives us 58.824 millihenries, a much more reasonable inductance value north. Ten thousand divided by 1 is 10 to the 4. 10 to the 3 would be 1,000. right? So 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 2 is 100. 10 to the 3 is 1,000. 10 to the 4 is 10,000. Okay. And then just to be clear, 2 times 50 is 100, so that's 10 to the 2 times 10 to the 3 is 10 to the 5. Not picking on you by any stretch of the imagination. I say that because I can remember sitting in 122 as an undergrad, thoroughly convinced that my teacher had done something like this wrong, and also was just like, that's wrong. And he's like, nope, it isn't. So anyway, so whatever. Sorry, not trying to be any more of a jerk than usual. L2. So same exact equation, Km over Kf times L2. So 10 to the 4 over pi times 10 to the 5 times 0.765 henries gets us 24.351 millihenries. C1 prime is going to be C1 divided by Km times Kf. So that's going to look like 0.765 farads divided by pi times 10 to the 9, 243.507 picofarads. And then lastly, C2 prime is going to be C2 divided by Km Kf. So 1.848 farads divided by pi times 10 to the 9 comes out to be 588.237 picofarads. So these are our values. Let's hope LT Spice or my Dropbox has synced up. If not, I'll just have to type this crap out. That'll be okay. So these are our two circuits. This is the normalized one. This is the scaled one. Everything look correct? Any of the values seem wrong or anything like that? So if I run this simulation and I look at V out 1, so we should see that our cutoff frequency is 1 radian per second, which would be 159 millihertz. Let me move this down here really quickly. So we can see that at very low frequencies, we're at a magnitude of -6 dB, which means our output voltage is roughly 1/2 of what our input voltage is, which would make sense because at very, very low frequencies, we have a simple voltage divider circuit where we're looking at the voltage drop over one of those 1 ohm resistors. Yes, sir. Yep. So anyway, our very, very low frequency magnitude is -6 decibels. So what we're looking for our cutoff frequency is -9 decibels, 3 dB lower than that. So I'm gonna bring this over, go, until it looks to be about -9. So like I said, somewhere in the ballpark of 159 millihertz. That's just 1/2 pi, no fancy magic or anything there. This was designed for 1 radians per second. Let's see that we have a drop of 3 decibels at effectively 1 radians per second. Now, coming over here, clicking on V out 2, changing the color to something more visible. And then looking over here. we have the exact same magnitude response and the exact same phase response. Now we should be looking for our output voltage to be at -9 dBs at approximately 50 kilohertz. So let's check that out. Where is the cursor for 2? I plugged in my keyboard, but I'm too lazy. There we go. A little bit below 9 decibels or -9 dB at a little bit above 50 kilohertz. So it's done exactly what we needed it to do. It replicated our frequency response entirely, both the magnitude and the phase. We simply shifted it by 50 kilohertz, or shifted our resonant frequency from 1 radian per second to 100 pi kiloradians per second. Everything else is literally identical. Yes, sir, Gabriel. Don't have to worry about like. So for this particular circuit, all I put in was just a 1 volt AC source so that my output voltage is my frequency response, because whatever V out is divided by 1 volt over all frequencies is just giving me my transfer current. I'm not looking in particular here for the voltage drop across any of the capacitors or anything, although we could look at those and see what kind of weird things we're going to get. So let's close that out. So let's see. I need my keyboard for this. So let's delete that one. Actually, I should have left that one, but that'll be okay. So if I want the voltage drop across my capacitors in my high frequency thing, let's get this crap out of the way. What the hell is happening behind me? There it goes. Rerun this. Get this out of the way. All right. Oh, and let's change the color of this guy to red again. So looking at this system, we can see that the voltage drop across our second capacitor never gets even to 0 decibels, meaning that it's never going to have even 1 volt across it. Right? So we are at slightly above -6 dB here because of the resonance, but it's not a huge amount by any stretch of the imagination. So we don't even put 1 volt across it. So that's probably going to be pretty damn safe. Over here, we have a voltage that is an output voltage that is about 0 decibels. So it's very close to 1 volt, but still not enough to warrant anything. Now, that being said, we made a passive network here meant to operate as a low pass filter. So it shouldn't have a whole hell of a lot of things going on. If this were a high Q bandpass filter, we might see something that would be worrisome. What we're going to be talking about later on this week will be active filters, meaning we're putting op amps and stuff in there to boost signals as well as filtering. And that's when we should probably start to be very diligent about component ratings and all of that kind of good stuff, because we're amplifying things. The whole point is to boost those signals, which might be in an unsafe-ish area. That being said, we are restricted to what the op amp can handle. right? So we know that the output of an op amp can never be larger than the supply voltages, so that's going to provide some limiting there as well to some extent. All right, hold on, Hannah. I don't fully understand the question. So we shifted the resonant frequency of the circuit because it was, all right, let me delete these things really quickly. Delete, delete. Look at the out, look at the in. Go back to this, change this color from green to red so that you can see it. So effectively, we shifted the entire frequency response over from here to here. Right? So that's the whole purpose of this, is to make our resonant frequency go from 1 radian per second which is what the red curve represents, to 100 pi kiloradians per second over here. Right? Now we also did magnitude scaling, but that's just scaling the impedances. It's not scaling the output of the filter at all. It's just scaling the impedances for what's available. So in our original circuit, we were using 1 ohm resistors. And for our second circuit, we're using 10 kilo ohm resistors. It doesn't change the shape of anything. It just makes it work for these particular values of source impedance and load impedance. So magnitude scaling is scaling the magnitude of these impedances, not the magnitude of the response. Yes, and that goes back to the equations, right? So if we look at the equation for the inductors, since we were doing both impedance scaling or magnitude scaling and frequency scaling, we have a ratio of Km over Kf that's applied to our inductors. So both are taken into account. And then we have C1 or C over Km times Kf because of how the math works out for our capacitors. The resistors, the frequency scaling factor is effectively just 1 regardless because they don't depend on frequency. So that's how, based on the information that we were given, let me scroll up here to the top, right? We wanted a new resonant frequency of 50 kilohertz. When I told you specifically that this one was designed to have a resonant frequency at 1 radian per second with 1 ohm resistance. We wanted 50 kilohertz using 10 kilo ohm resistors. So we could do something similar to this, but we could say, you know what, I only have 47 nanofarad capacitors available. What values of resistors will I have to use? Or what values of inductors will I have to use to shift the frequency to this 50 kilohertz or something like that? So the constraint for this design problem was that our resonant frequency shifted to 50 kilohertz and that we had to use 10 kilo ohm resistors. All right, so we'll do more of this, look at filters and all that kind of jazz in class on Wednesday. I hope to be able to get the table and all that kind of stuff made out so that we could just refer to that and make our lives easier. Anyway, all right, see you guys on Wednesday.